Let's suppose that we hang or suspend a flexible spring vertically from a rigid support. This spring has a natural length of L. Now let's suppose that from this we attach a mass M. It's now going to extend a little bit further down. Let's call that extra distance S. Now, springs follow what's known as Hooke's law, which states that the spring will exert a restoring force in the opposite direction. So in this case, the spring's being elongated, it's being pulled down by this mass. So it's going to exert a force in the upwards direction. And this restoring force is proportional to the amount of elongation, S. So the restoring force is equal to some constant K times S. K is the spring constant. And S is, of course, length of elongation or compression. A positive value of S will represent elongation. A negative value represents compression. Now this new length let's call it X, doesn't matter. This is the equilibrium position. It simply represents the point at which the force of gravity matches the restoring force. So hence the spring is no longer elongating. This means, of course, that F would have to be equal to the force due to gravity. The restoring force is the force due to gravity. So Ks is equal to mg, or mg minus Ks has to be 0. Now let's suppose that we take this mass M, we pull it down a little bit and then release it. So we're setting the spring into motion. So it's going to have an initial displacement and it's going to have an initial velocity. X of t will be the displacement. So we will let x of t represent displacement. X naught will be the initial displacement. I'm sorry, x naught. X equals 0 will represent equilibrium. X greater than 0 will be elongation. To study this motion, we're going to apply Newton's second law. Which states that the sum of all the forces acting on an object is equal to mass of the object times the acceleration. Furthermore, we're going to assume there are no external forces. In other words, once we set this spring into motion, so once we give this M an initial displacement and release it, there's going to be no extra forces working on it. This kind of motion is known as free motion. So, what we're going to wind up with is M times A, which is M times X double dot. This will have to equal mg minus ks, I'm sorry, k times x plus s. So we have mg minus kx minus ks. But if we take mg minus ks, that is equal to 0. And so we're left with negative kx. In other words, ma, mx double dot, has to equal negative kx. This means that mx double dot plus kx is 0. Putting this into standard form, we're going to get x double dot plus k over m times x is equal to 0. We will replace k over m and say that is omega squared. And so we'll write the equation as x double dot plus omega squared x is equal to 0. This describes what is known as simple harmonic motion, or, as we'll be calling it, free undamped motion. We're now going to solve this differential equation. Now we know how to solve this. Second order, so we're going to have m squared plus omega squared is equal to 0. And so m is plus or minus omega I, which means that the solution will be C1 cosine omega t plus C2 sine omega t. But as was stated previously, we have initial conditions. We have an initial displacement, let's call it x naught. We have an initial velocity, let's call it v naught. Now remember, velocity is the first derivative of displacement. So this is x dot of 0. We have x dot of t is equal to negative c1 omega sine omega t plus c2 omega cosine omega t. So using the initial conditions, x of 0 has to be x naught. We get c1 cosine of 0 plus c2 sine of 0. Of course, sine of 0 is 0. So from this, we find that c1 is simply x naught. X dot of 0 has to be v naught. So negative c1 omega sine of 0 plus c2 omega cosine of 0. And again, sine of 0 is 0. And so c2 is v naught over omega. And so our model for free undamped motion is x of t equals x naught cosine omega t plus v naught over omega sine omega t. The period of motion is given by t equals 2 pi over omega. So the period is the time it takes for the spring to execute one full cycle of motion. So if this is our motion right here, the period is how long it takes for M to go down, up, and then back down into its original position. The frequency is given by F, which is omega over 2 pi. Frequency represents the number of cycles completed each second, and we call omega the circular frequency of the system. It is very rare that we have no external forces acting on a system. We will now look at what happens if we have what's known as a damping force, or in a sense, friction. So, where we know that we have the force of gravity, and we also have the restoring force. I'm now going to call this F sub S for the restoring force. Now we also are going to have a damping force. call it FD. Now the damping force also acts in the opposite direction of motion. So we now have three forces to consider. Force due to gravity, which is mg. We have the restoring force, which is governed by Hooke's law, so ks. And we have a damping force. Now, we shall assume that the damping force is given by a constant multiple of the instantaneous velocity, so beta v. We call this beta the damping constant. And we take it to always be greater than 0. If it is 0, then we have no damping constant, or we have no damping force. So with all this in mind now, if we now put the spring in motion, then Newton's second law is going to give us mx double dot is equal to negative kx minus beta x dot. So we're going to have mx double dot plus kx plus beta x dot is equal to 0. Put this in standard form. X double dot plus beta over m x dot plus k over m x is equal to 0. We will now define beta over m to be 2 lambda. And again, we'll keep k over m as omega squared. This will give us the equation x double dot plus 2 lambda x dot plus omega squared x is equal to 0. This is the equation for free damped motion. We now want to solve this. So the auxiliary equation, m squared plus 2 lambda m plus omega squared is equal to 0. This will give us two solutions. m1 negative lambda plus the square root of lambda squared minus omega squared, and m2 negative lambda minus the square root of lambda squared minus omega squared. So we have three cases. We could have lambda squared minus omega squared greater than 0. We could have lambda squared minus omega squared being 0. Or we could have lambda squared minus omega squared being less than 0. We are going to study each of these three cases individually. First, we consider if lambda squared minus omega squared is greater than 0. We call this case overdamped. And the reason is the damping coefficient is large compared to the spring constant. Now this case is equivalent to the two distinct real roots case. So our general solution will have the form C1 e to the m1, which will be negative lambda plus the square root of lambda squared minus omega squared, all times t, plus C2 e to the negative lambda minus the square root of lambda squared minus omega squared, all times t. This can be simplified. We can pull out an e to the negative lambda t, and then we're left with C1 e to the t times the square root of lambda squared minus omega squared, plus C2 e to the t times the square negative t times the square root of lambda squared minus omega squared. We now wish to find the C1 and C2. So x dot e to the negative lambda t times C1 times the square root of lambda squared minus omega squared e to the t times square root lambda squared minus omega squared minus C2 square root lambda squared minus omega squared e to the negative t square root lambda squared minus omega squared. Then we're going to have minus lambda e to the minus lambda t times C1 e to the t square root lambda squared minus omega squared plus C2 e to the negative t square root lambda squared minus omega squared. So x of 0 is our initial displacement, x naught. So we're going to get, plug everything in to here, e to the 0 times C1 e to the 0 plus C2 e to the 0. So we get C1 plus C2. X dot of 0, remember, is our initial velocity, v naught. So we plug that into this equation. We get e to the 0 times C1 square root lambda squared minus omega squared, e to the 0 minus C2 square root lambda squared minus omega squared, e to the 0 minus lambda e to the 0 times C1 e to the 0 plus C2 e to the 0. So we're going to have C1 square root lambda squared minus omega squared minus C2 square root lambda squared minus omega squared minus C1 lambda minus C2 lambda. So it's the square root of lambda squared minus omega squared minus lambda times C1 minus square root of lambda squared minus omega squared plus lambda times C2, and then that whole thing equals V naught. This gives us a system of equations. C1 plus C2 has to equal x naught. Then we have square root of lambda squared minus omega squared minus lambda C1 minus square root of lambda squared minus omega squared plus lambda C2, and that has to be V naught. We need to solve this system. So the first thing we can do is eliminate the variable C2. This will give us 2 square root of lambda squared minus omega squared. C1 is equal to the square root of lambda squared minus omega squared plus lambda x naught plus V naught. And so C1 winds up giving the square root of lambda squared minus omega squared plus lambda all over 2 square root of lambda squared minus omega squared x naught plus 1 over 2 square root lambda squared minus omega squared all times V naught. So this means that this term plus C2 has to be x naught, and so C2 is the square root of lambda squared minus omega squared minus lambda all over 2 square root of lambda squared minus omega squared x naught minus 1 over 2 square root of lambda squared minus omega squared V naught. So our equation for free overdamped motion, or I'm sorry, our model for free overdamped motion, x of t equals e to the negative lambda t times C1 so the square root of lambda squared minus omega squared plus lambda over 2 square root lambda squared minus omega squared x naught plus 1 over 2 square root lambda squared minus omega squared V naught e to the t square root of lambda squared minus omega squared plus square root of lambda squared minus omega squared minus lambda all over 2 square root lambda squared minus omega squared x naught minus 1 over 2 square root lambda squared minus omega squared V naught e to the negative t square root lambda squared minus omega squared, and I'm out of room. So I'm going to rewrite it. And so this is our equation for free overdamped motion. We next consider the case where lambda squared minus omega squared is 0. This case is known as critically damped, because any slight decrease in the damping force would result in oscillatory motion. Now, notice that this case is repeated real roots. So our general solution will have the form C1 e to the negative lambda t plus C2 t e to the negative lambda t, which is e to the negative lambda t times C1 plus C2t. Now x dot would be e to the negative lambda t times C2 minus lambda e to the minus lambda t times C1 plus C2t, which equals C2 e to the negative lambda t minus C1 lambda e to the minus lambda t minus C2 lambda t e to the minus lambda t. X of 0 is x naught, so this equals e to the 0 times C1. So C1 is simply x naught. X dot of 0, C2 e to the 0 minus C1 lambda e to the 0 minus 0. So this winds up being C2 minus lambda x naught, which means that C2, sorry, this whole thing has to equal V naught. And so C2 is lambda x naught plus V naught. So our free critically damped motion is explained by x of t equals e to the negative lambda t times x naught plus V naught t. I'm sorry, that's wrong. It's x of t equals e to the negative lambda t times x naught plus lambda x naught plus V naught times t. We now consider the final case where lambda squared minus omega squared is less than 0. This is known as underdamped. This is because the damping coefficient is small compared to the spring constant. Now, since lambda squared minus omega squared is less than 0, omega squared minus lambda squared will have to be greater than 0. So we can write the square root lambda squared minus omega squared as the square root of negative omega squared minus lambda squared, which is I times the square root of omega squared minus lambda squared. Notice that this now gives us complex conjugate case. So our general solution will be of the form C1 e to the negative lambda t cosine of t times the square root omega squared minus lambda squared plus C2 e to the negative lambda t times the sine of t times the square root omega squared minus lambda squared. Which we can rewrite by factoring out e to the negative lambda t. Using the condition x of 0 is equal to x naught, we'll have x naught is equal to e to the 0 times c1 cosine of 0 plus c2 sine of 0, which is just c1, so c1 is x naught. We now need the derivative, so x dot of t, we'll get e to the negative lambda t times negative c1 square root of omega squared minus lambda squared times sine of t times that square root plus c2 times the square root times cosine of t times the square root minus lambda e to the minus lambda t times c1 cosine plus c2 sine. So using the condition that x dot of 0 is v naught, we get e to the 0 times negative c1 square root sine of 0 plus c2 square root cosine of 0 minus lambda e to the 0 times c1 cosine of 0 plus c2 sine of 0. So we'll wind up with c2 times the square root minus lambda x naught, and that has to equal v naught, and so c2 has to be lambda x naught plus v naught all over the square root. And so our free underdamped motion is described by the equation x of t equals e to the negative lambda t all times x naught cosine of t times the square root plus lambda x naught plus v naught all over the square root times the sine of t times the square root. Notice that in all three cases, the general solution had the term e to the negative lambda t. This is called the damping factor. Now, the motion of the mass will become negligible as t approaches infinity in all three cases. That is because this term, the damping factor, will tend to 0 as t tends to infinity. So this is damping. So the fact that it's being damped means that the motion will eventually dissipate. It just takes a very, very long time. Let's now consider what happens if the spring is subject to an external force. Let's say it's attached to a motor. So we're adding an extra force, let's call it F of t, a driving force. Then Newton's second law will give us mx double dot is equal to negative kx minus beta x dot plus this F of t. If we put this into standard form, we'll get x double dot plus 2 lambda x dot plus omega squared x is equal to capital F of t, where again 2 lambda is equal to beta over m, omega squared is equal to k over m, and capital F of t now is equal to little f of t divided by m. This is the equation for driven motion or forced motion. So to solve this equation, we'll use the techniques for the free damped motion. That'll give us our complementary solution, xc of t. This is called the transient solution. We would then use either undetermined coefficients or variational parameter to find our particular solution. This is called our steady state solution. And then the general solution is just the sum of the transient and the steady state. Now the reason that this is called the transient is, as we've seen, as t goes to infinity, this will go to 0. So as more time passes, this term becomes negligible. And that's why this is called the steady state, because as time goes on, the motion will be completely described by our particular solution, xp. And so it's a steady state. So we're going to find the equation of motion for the forced spring given by x double dot plus omega squared x is equal to f naught sine of gamma t, where the original displacement is 0 and the initial velocity is also 0. Now we look at this and we go, well, this is undamped. So the transient solution would be C1 cosine omega t plus C2 sine omega t. We have to find the steady state now. Well, notice that our big F of t is some constant f naught times sine of gamma t. So the steady state will have the form a cosine gamma t plus b sine of gamma t. So x dot negative a gamma sine gamma t plus b gamma cosine gamma t, and x double dot negative a gamma squared cosine gamma t minus b gamma squared sine gamma t. So we plug this now into our original equation. So we'll get negative a gamma squared cosine of gamma t minus b gamma squared sine of gamma t plus omega squared times a cosine gamma t plus b sine gamma t. We want to simplify this. So this equals, bring all of our cosine terms together. We'll get omega squared a minus gamma squared a cosine of gamma t plus now our sine terms. We get omega squared b minus gamma squared b. And this has to equal f naught sine of gamma t. This will give us a system of equations. We get omega squared a minus gamma squared a is equal to 0, and omega squared b minus gamma squared b is equal to 0. This first equation implies that a has to be 0. I'm sorry, this is not 0. The second equation is f naught. Then this equation implies that b has to be f naught over omega squared minus gamma squared. So our steady state solution is simply f naught over omega squared minus gamma squared times sine of gamma t. And so our general solution, C1 cosine omega t plus C2 sine omega t plus F naught over omega squared minus gamma squared sine of gamma t. We're going to need the first derivative of this, so we get negative C1 omega sine omega t plus C2 omega cosine omega t plus F naught gamma over omega squared minus gamma squared cosine of gamma t. So using x of 0 being 0, we get C1 cosine of 0 plus C2 sine of 0 plus F naught over omega squared minus gamma squared sine of 0. This is just C1, and so C1 has to be 0. X dot of 0 is also 0. Well, I already said C1 is 0, so I'm going to cancel out this first term. So we get C2 omega cosine of 0 plus F naught gamma over omega squared minus gamma squared cosine of 0, which is just C2 omega plus F naught gamma over omega squared minus gamma squared. And this, of course, has to be equal to 0. And so C2 would equal negative F naught gamma divided by omega times omega squared minus gamma squared. So our solution, our motion, will be described by F naught over omega squared minus gamma squared sine of gamma t minus F naught gamma over omega times omega squared minus gamma squared times sine of omega t, with the condition that omega cannot equal gamma. Otherwise, we'd be dividing by 0, and we can't do that. We conclude this lesson by looking at an LRC series circuit. Remember, I of t will denote the current. Kirchhoff's second law will then give us L di dt plus Ri plus 1 over CQ has to be E of t, where Q is the charge. These should be capitalized. But remember, current is simply derivative of charge. So we can rewrite this. LQ double dot plus RQ dot plus 1 over CQ is equal to E of t. Now, if E of t is 0, the electric vibrations are said to be free. So we have a homogeneous equation in this case. So the auxiliary equation will be Lm squared plus Rm plus 1 over C is equal to 0. This will give us the roots. M1 is negative R plus the square root of R squared minus 4L over C all over 2L, and M2 is equal to negative R minus the square root R squared minus 4L over C all over 2L. As with the spring system, we have 3 cases. If R squared minus 4L over C is greater than 0, the system is overdamped, and we have a transient solution. QC is equal to E to the negative RT over 2L times C1 E to the square root of R squared minus 4L over C over 2L plus C2 E to the negative, there should be a T there, negative square root R squared minus 4L over C over 2L T. If R squared minus 4L over C is equal to 0, the system is critically damped, and we have the transient solution. E to the negative RT over 2L times C1 plus C2T. Finally, if R squared minus 4L over C is less than 0, the system is underdamped, and we have the transient solution E to the negative RT over 2L times C1 cosine T times the square root 4L over C minus R squared plus C2 sine times T square root 4L over C minus R squared. If both E of t and R of t or not R of t, but R equals 0, this is undamped. And if E of t is not 0, the system is forced. Then we'd have 2 solutions. You'd have the steady state QC and, the steady state QP and the transient QC. that concludes this lesson. I hope you've learned something, and we'll see you in the next one.